All right. I'm making the video today in this hour instead of at another hour because something happened with my video yesterday, and I want to know if I fixed it, and if it didn't fix it, then I'll make the video later. So, hey, good times. Anywho, we're going to talk about phase change calculations in this lesson, and in order to talk about phase change calculations, we need to kind of go back in time and not rehash, but focus in a little bit more on energy phase change in general. When there's a phase change, that is, a solid is going to a liquid, or a liquid is going to a gas, or in something in that capacity, there's always some type of energy that is either being added or removed that causes that change. And so, but when that happens, the actual temperature of the object stays at that temperature until all of the particles of that substance have changed from, say, a solid to the liquid form. Now, there are some fun new vocabulary that we're going to talk about. And the first one we're going to talk about is something that we call heat of fusion. Heat of fusion is the amount of energy needed to melt or freeze 1 mole of a substance. So if we are melting a substance, I would like to kind of try to write out a little bit of a timeline, or maybe not a timeline, but maybe some type of a flow chart or graphic organizer to help you keep in mind of what's actually happening. This might become super helpful, and you might refer back to it often. So if we melt a substance, you have to remember that you are going from a solid to a liquid. And when you melt something, you're generally adding energy, so that's going to be endothermic. Now, the next part of this that's really important is this heat of vaporization, heat of fusion, or delta H fusion, will have a positive value, a positive numerical value. And again, remember, this is energy added. I'll just say energy in. Now, the opposite of melting is freezing. And that's when you go from a liquid to a solid. And that process is exothermic. Now, in this instance, the value of the heat of fusion has to be negative. And that will tell you that energy is out. Yes.
Are we not doing vaporization? When it goes from a liquid to a gas?
Heat of vaporization is what we're going to talk about next. So the heat of fusion, when you think about the term fusion or fuse, that usually relates to putting things together, right? Hopefully. And the opposite of fusing would be taking things apart. So the heat of fusion is when we're thinking really around the solid and liquid phase change. Okay. Now, heat of vaporization, which is what you were getting at, is the amount of energy needed to boil or condense 1 mole of a substance. Okay. So when we talk about this idea, when we boil something, we are going from a liquid to a gas, and that will be endothermic. And so that delta H, the heat of vaporization, will be a positive value, and again, energy in. And technically speaking, the opposite of boiling something would be to let it condense. And so that's when you go from a gas to a liquid. That is going to be an exothermic system. And in that one, the delta H, or heat of vaporization, will have a negative value, and that again will be energy out. Now this flowchart or graphic organizer will be valuable when we get to the math, the second part of the math part for this particular lesson. So we'll come back and visit this question.
Yeah, what's like an actual like situation of like condensing? Would it be like a lid on like a boiling pot of water?
That's exactly so. An example of something condensing would be if you have a boiling pot of water and maybe you turn the heat off, but you put the lid on it and you see the droplets of water forming on the lid. That's where the steam, the gaseous form of water would condense and turn back into a liquid. Yes. The question is, are we going to do anything with sublimation? The answer to that question is we are not going to do math with it, but we are going to discuss it. Okay. So, speaking of math, let's talk about this math. Now, in this instance, right, what I'm seeing is that the problem is telling me we are going to melt something. Okay. And so in my head, if we are going to melt something, that means that we are going to go from a solid to a liquid, right? And if we're going to go from a solid to a liquid, that tells me also that I'm going to need the heat of fusion. Okay. And just to kind of reiterate that, going back up, we're melting solid to a liquid. This says it's endothermic. That means our delta H, heat of fusion, has to be positive. So we'll come back to that whole idea, but we're going to do the math first. So in this case, I'm going to take 15 grams of water, because that's what ice is, right? And I'm going to go mass. Well, let me get it. I get a little bit ahead of myself. Okay. The heat of fusion has a unit, right? And that unit is kilojoules in 1 mole. Okay. So that's heat of fusion. That's its unit. Okay. Kilojoules in 1 mole. If I have grams or mass of ice, what should I convert grams or mass of ice to in order to get to energy kilojoules? What should I convert my 15 grams to so that I can eventually get to kilojoules? Moles, right? So I'm going to go mass to moles and moles to eventually energy. And when I go mass to moles, I need to know the molar mass, right? So I'm going to take 2 hydrogens times 1.01 grams, which will give me 2.02 grams. And I have 1 oxygen times 16.00 grams, which will give me 16.00 grams. I add all that business up and I get something like 18.02 grams in 1 mole of water. So now I'm going to take that relationship and convert grams of water to moles of water, which means I'm going to put the 02 grams of water on the bottom and the 1 mole of water on the top. And again, because we're melting, we're going through the phase change of melting, we're going to use delta H, the heat of fusion. And it just said that that's kilojoules per mole. So I'm going to put 1 mole of water on the bottom, and I'm going to put 6.01 kilojoules on top. Now, again, I'm going to scroll back up to that graphic organizer, that flow chart real quick once to make sure I have the right sign convention for kilojoules. So in this case, melting, solid to a liquid, endothermic, the delta H value has to be positive, so I'm going to leave it alone. So now all that's left to do is to grab my calculator and calculate this out. So I'm going to take 15. I'm going to divide it by 18.02. I'm going to take that answer and multiply it by 6.01. That's going to give me a calculator value of 5.00277 ... Okay. Looking for significant figures in this problem, I have 1, 2, 3 sig figs here. I have 1, 2, 3, 4 sig figs here. And I have 1, 2, 3 sig figs here. So my final answer should have 3 sig figs. That 2 does not round that 0 up. So my final answer is going to be 5 kilojoules of energy. And you wouldn't necessarily put kilojoules of water because that's not really what we're dealing with here. We're just going to be dealing with the amount of energy. Questions? Hopefully you're like, oh, the math isn't too bad. The new math. All right. So is this an endothermic or an exothermic process? Going back up to our flow chart, we said that it is going to be endothermic, but we also need to have a little bit more of an explanation. So this is going to be endothermic. And I'm going to say because we're putting energy into the system, so energy is added to the system to weaken the intermolecular forces of attraction. And so when we weaken the intermolecular forces of attraction, we result in a change of state or phase from solid to a liquid. So this results in a phase change from a solid to a liquid. So the explanation here is like twofold. We're talking about what's happening in terms of intermolecular forces of attraction, but then we're also talking about the phase change and what the phase change specifically is. So I would like to do a you try for example number 2. I know you can do it. I believe in you. You can do it. So we're gonna do it together, but you're gonna do it and they're gonna come back to it. So here we go. Here's example number 2. Give this one the old GHS try. Ready, set, calculate. So in this problem, you are asked to figure out the amount of energy released when 22 grams of water condenses. So now we're dealing with condensation. So we are condensing. And again, we're going to go from mass to moles of water, and then we're going to go moles to energy of water, right? And in this case, we will be dealing with the heat of vaporization this time, because even though it's condensing, it's not becoming a gas, it's going from a gas to a liquid. And when it's going from a gas to a liquid, what ends up happening is we have to use the heat of vaporization value, but that value must be negative. Questions? Yes.
Why isn't it negative on the chart?
Oh, that's a good question. The question is, why isn't the value negative on the chart? And the answer to that question is because that's just the value of the amount of energy that is either being released or added during that particular phase change. We change the convention of the sign based on what's happening. So I guess another way to write the chart would be you could have delta H fusion negative 6.01 and delta H fusion 6.01. And you could have delta H vaporization negative 40.7 and delta H vaporization 40.7. But it just becomes a little bit less cumbersome in terms of a chart to remember that you have to be aware of when to use the sign. So again, this one, the reason why that's important is because of what's actually occurring in the problem. So the next question that we're going to talk about here is this an endothermic or an exothermic process? And so we should be able to identify that this is going to be an exothermic process. Yes. I don't want to talk about it. This is exothermic because, right, energy is being released. Is being released as intermolecular forces of attraction are being formed. And as a result of those intermolecular forces of attraction being formed, this results in a gas in a phase change of a gas to liquid. So again, the explanation is like twofold. We're talking about energy and what's happening in terms of intermolecular forces of attraction, and then we're talking about the phase change, in this case, from gas to liquid. Questions about this? Okay. Now, the reason why we talked about the heat equation yesterday and we're talking about the phase calculations today is because we are going to kind of mash them all together in this part of the lesson. So let's talk about this for a second. This is known as the heating curve of water. If you take a solid chunk of ice and you start adding heat to it, and you will take that one chunk of ice and eventually vaporize it and make it into gaseous water, right? It will go through the same steps no matter how much ice you have. The graph will look like this no matter how much ice you have. So I want to kind of take a minute or two here and just kind of explain what's going on here. So when you're down here, hopefully you can see on your paper or in your note sheet or whatever that we're below zero at that point there. That is like negative 50 degrees Celsius to like 0 degrees Celsius. And what state of matter would we be in at that point? We'd be freezing, so it'd be a solid, right? But if you start at 0 on the heat absorbed axis and you start adding temperature, like, I don't know, let's say it looks like they added like maybe 100 kilojoules of energy, the temperature of the substance started to warm. So in this instance, this part right here is a thermal change. We are heating or warming a solid. Okay. And when you get to the next part, it looks like that plateaus a little bit. Like the temperature stays the same for a period of time or a period of amount of energy that's being added. And so at that point, the temperature is staying the same, but what's actually occurring is a phase change, and that's going from a solid to a liquid. What you should be paying attention to here is the idea that there is a period of energy being added where this substance, this chunk of ice is melting. It's becoming a liquid, but the temperature doesn't increase. And that's a state that is a true observation, that when you take a chunk of ice and you let it melt, whether it's on the table or you put it into a pot of water or you put it into a pot and you turn the heat on, the temperature will stay the same until all of that solid has converted to liquid. This next part right here is another thermal change. Here we are simply heating a liquid. And you might have witnessed this or lived this when you make the macaroni and cheese, right? You put the pot of water on the stove and you turn it on and you wait and you wait and you wait and you wait, and the liquid feels like it takes forever to get to that boiling point where you can start adding the noodles in, right? Okay. That, hopefully, what this graph is illustrating is a very similar situation. There is a lot of energy that has been added to get to the boiling point. Hopefully you can see. Now, the next part of this is another plateau, another flat spot. And this plateau or flat spot is another phase change. This is when a liquid is being converted into a gas. So in this case, again, we've warmed the liquid water up to 100 degrees Celsius, and now we are adding an incredible amount of energy over time until all of that water eventually vaporizes and becomes a gas. At that point, once all of the water has vaporized and it's a gas, if it's in a closed system, we can continue to warm it, and we can have a thermal change where we are simply heating a gas. Okay. Now, this heating curve is specific for water, but the actual shape of a heating curve for almost every substance will look very similar. You take a solid substance, you warm it until it gets to its melting point, and then it stays at that temperature until it completely melts. You take that substance at its melting point, and you continue to add energy to it. It will continue to warm until it gets to its boiling point. And then once you get it to its boiling point, you continue to add energy to it, and it will all eventually become a gas. And then you could, in a closed system, continue to warm that gas. So, lots of energy. When we are doing these problems, we're going to be going through a series of steps. And the series of steps are basically, you have to identify the temperature range, that is the thermal energy that the substance is going through. What we're really looking at here is we're looking at the T initial versus the final temperature. Okay? That's really what we're looking at here. Then we have to decide if the substance is going through a boiling point or a melting point or both. So is it freezing? Is it condensing? Is it melting? Is it vaporizing? Okay. And then each energy transition within the temperature change will require a thermal energy calculation. And that's this formula here, where heat is equal to mass times specific heat times change in temperature, like so. And then each energy transition with a phase change, remember going solid to a liquid, liquid to a gas, would be a mass to mole to energy calculation. And then eventually, depending on the number of calculations you do, you'll be adding them up for a total value. So let's do one. And this is where I'm going to hear a lot of sad complaining, and I'm just going to say it is what it is. So here we go. Holy moly. So how much energy is released when 100 grams of liquid water at 25 degrees Celsius is changed to ice at negative 10 degrees Celsius? So I'm going to draw a real quick graph once to help me see what's going on here. So if we're talking about the heating curve of water, it looks something like this, right? Our initial temperature is this, and our final temperature is this. So far, so good. Thinking back to the heating curve of water, right? At 1, 2, 3, 4, or 5, right? Where would we be on this heating curve, 1, 2, 3, 4, or 5, if we started at 25 degrees Celsius? We would definitely be at 3. So 25 degrees Celsius would be something like here. That's our T initial. Okay, and I should probably blow this up so you can see that better. Okay, where will we be on this heating curve if we end at negative 10 degrees Celsius? We'd be at 1, right? So we'd be somewhere down here. So this is going to be TF. So what this tells me is we are going to go, this substance is going to go from a liquid, and then it's going to eventually convert to a solid. Okay? So we're going to have to do a series of calculations where we are cooling, so that we're going to go thermal. And then we are going to go phase. And then we are going to go thermal again. So the calculations that we are going to have to do are 3 different calculations. So I'm going to shrink that down a little bit so I can do some work. See what this gentleman has to offer. Yep. Autumn. Now, so here we go. The first one that we have to do is we have to do a thermal change because we're starting at liquid and we're going to, and we're cooling it down, right? So first calculation is going to be Q and mass and CP, and it'll be TF and TI, okay? So now in this instance here, I know a couple of things are pretty easy to find. I have 100 grams of water. Now the CP in this case, right? The CP in this case is I'm at water and we've already decided that we're liquid, so I need to use this one. So I'm going to use the 4.18, and that'll be joules over grams times degrees Celsius. And now my initial temperature, right, is 25 degrees Celsius. But if we're going from a liquid to a phase change, right, what's my final temperature going to be? Yes.
Do we need the final temperature there? I mean, wait, the other one, the delta temperature?
Well, I'm combining that. Oh. Okay. So, what's the final temperature going to be for this calculation? Yes, it's going to be 0. It's going to be 0 because we are cooling it from 25 degrees Celsius to its freezing point. So when I plug this in, I'm going to have Q is equal to mass times specific heat times, in this case, the change in temperature, which will be TF minus TI. So I'm going to plug in what I have. So in this case, the mass is 100 grams. The specific heat is 4.18, and that's going to be joules over grams over degrees Celsius. And then my change in temperature here is going to be 0 degrees Celsius minus 25 degrees Celsius. I'm going to plug this into my calculator and get a value. So I'm going to have 100 times 4.18 times negative 25. And the calculator is going to tell me that my value here for the heat is negative 10,450 joules. Now, what I would like to point out is that I've already kind of mentioned that the currency, or maybe I didn't, the currency of money in the United States is the dollar, correct? The currency of energy in chemistry and physics is the kilojoule. So we need to convert this value to the kilojoule using the relationship 1 kilojoule equals 1,000 joules. So I'm going to do that real quick once over here. And that's going to give me a value of negative 10 point, it says 450, but there's 3 sig figs, so I'm going to take 10.5 kilojoules. And that's 1. Calculation 1. Olivia? Okay. So calculation 1 was my thermal calculation. Pardon? To kilojoules? Because the thing of it is that, see how the heat of fusion has a value in kilojoules? The more accepted way to report energy in chemistry and physics is in the kilojoule. And eventually we're going to add all these calculations together, so they should be in the same unit. So my next calculation will be a phase calculation, which is the one we just learned about today. And again, that's going to go mass to mole to energy. And when we do that, I'm going to start with the 100 grams of water. And we've already calculated in this lesson the molar mass of water, so I'm not going to redo that, which is 18.02 grams of water here in 1 mole of water. And now we are going from a liquid to a solid, so we're going to be using the heat of fusion. And the heat of fusion, because this is in a relationship where energy is being released, the heat of fusion has to be negative. So this is going to be a negative 6.01 kilojoules in 1 mole of water. So I'm going to take 100 times negative 6.01 divided by 18.02, and I get something like negative 33, let's say 0.4 kilojoules. So now we've gone from, on our heating curve, the liquid portion, and we've gone all the way through, and now we are a solid chunk of water, and we need to go do one more calculation, which is a thermal calculation, okay, to finish this one out. So this is going to be Q mass, which is still 100 grams. The CP in this case, because we're now at a solid, is going to be this one. So it's going to be 2.09 kilojoules per mole. Nope, CP. I lied. It's going to be joules per grams per degree Celsius. And then the change of temperature, the TF, and the TI. In this case, we're finally going to get to that negative 10 degrees Celsius, and our initial temperature is going to be 0 degrees Celsius. So I'm going to plug things in. Mass times specific heat times TF minus TI. So my mass again is 100 grams. The CP is going to be 2.09. And remember, that's going to be joules over grams over degrees Celsius. And the change in temperature is going to be negative 10 degrees Celsius minus 0 degrees Celsius. So when I plug this in, 100 times 2.09 times negative 10, I get a Q, or a heat value, to be negative 2090. All right, so we got right up to the end of the hour there, and what I want to make the point of here to wrap this one problem up is this is going to be negative 2090 joules. But again, because kilojoule is the currency of energy in chemistry and physics, I'm going to convert it to kilojoules. And when I do that, I get negative 2.09 kilojoules. Now, the last part that we have to do here is we're going to simply add these up. So the total energy will be the sum of the three calculations. So our first calculation had a value of negative 10.5. So it's going to be negative 10.5 kilojoules. Our second calculation had a value of negative 33.4 kilojoules. And our third calculation had a value of negative 2.09 kilojoules. So when we add all of those up, we get negative 10.5 plus negative 33.4 plus negative 2.09. And we get something like a value here to be like negative 45.99 kilojoules, which with 3 sig figs, which is pretty much what we've been carrying all the way through here, will end up being negative 46 kilojoules total. And so that's how we do a problem where we would go from where you would do a thermal calculation, a phase calculation, and a thermal calculation. And on Monday, we will go over the other example, and then you'll have some work time. So that's today's lesson.